All right, let's talk about power now. Power is the rate of work done, or the rate of energy expended by an object. Now, that rate should automatically mean to you something divided by time. So work divided by time, or energy expended divided by time. Rate of work done, rate always generally means time. So the equation for power, power equals work divided by time, or it's actually the exact same thing. We haven't fully gotten into this yet, but it'll be energy divided by time. Okay, so work divided by time, or energy divided by time. Now work, we know the equation for that, right? We can break this equation down. Let me choose a different color. Power equals, now work, the equation for that is F delta X, right? F delta X over T, right? And so if you can figure out the force that it takes and how far it goes, delta X, so force it takes to apply, to push the thing, delta X, how far it goes, time, how long it takes to do it, you can get power. Power is how quickly, if you will, you are doing work. If you're exerting a lot of power, you're doing something very fast, especially if you're doing something very hard, requiring a lot of work, very fast. That's generating a lot of power. Because you can do things that require a lot of work, a lot of force times displacement, but if you do it very, very slowly, you're not going to push, you're pushing and you're trying to do it very slowly, that doesn't require tons of power. You can get away with a low amount of power, or a low-powered engine, if you will. That's kind of envision where we're going here. Just a few more thoughts. Well, force can be broken down into whatever it is, right? So force can be broken down into, let's say, gravity, if you're going against gravity, mg, and I'm going to replace with delta y here if we're going straight up over time, right? If you're lifting something up at a constant velocity, remember that from previous times, the weightlifter, right? mgh delta y. Now, all that's interesting. You're actually going to do a lab where we're going to go upstairs, and you're going to have to calculate how much power you generate while running up the stairs trying to get your best time, your highest powers. Anyway, all that's well and good, but that's not really where the power equations get interesting. Power equations get very interesting whenever we start combining things and we get rates. So for example, here's two things where we could get a rate out of this. Now power equals a force times a displacement divided by time, right? What though is displacement divided by time equal to? Well, displacement divided by time is equal to velocity. That's the equation for velocity. So another way to write the power equation would be power equals force times velocity. So how hard the force you're having to apply, how hard you're pushing, times the speed the object is going at, right? So you apply so much force and it causes to go so far. Here's another interesting way to look at power. Right, if we break it all the way down, let's say we're trying to lift something straight up, so we know gravity, right, mgh, or maybe it's something else, mg delta y if we're pushing something, or delta x if we're pushing water through a pipe, or anything. We could take this mass over time and group it together, right? So the mass from the force that would get broken down, right, force turns into mg if it's going straight up, mass times gravity. We could break that down. What if we group the mass and the time together? Well, this would be how much mass you're able to move per second. That's very useful in things like with liquids, flow rates. We need to pump 2 kilograms per second. That's a lot of water, by the way, but 2 kilograms per second through this pipe. A good flow rate would go in there times gravity times how high up you're trying to pump the water up into the water tower, or whatever you're trying to do. So these ideas of rates are very, very useful. All right, so I'm going to skip the plug-chug problems where it's just power equals work divided by time, and then you got to break work into force times displacement. Maybe you have to find force and you just solve through there. I'm going to skip that. That's more of a plug-chug. I think you're okay with that. You know how to solve work problems, right? So the only addition for a power problem is you solve the work problem, then you divide by time, and you got power. So that's pretty straightforward. I want to jump straight into these problems dealing with rates. So here I've got a moving sidewalk with a known power for motor, 2,100 watt motor. And I can't remember if I told you the units for power in the previous slide. I think I didn't, which is my mistake. The units for power is the watt, okay? It will be abbreviated capital W. That's the units for power. So, unit power. Okay. So unit for power is watts. So I know a motor, 2,100 watt motor, can apply a maximum of 1,050 newtons. At what velocity does it move people along? So it's an airport moving sidewalk, right? You hop on it and it takes you along. People really use this to go twice as fast, right? Because if you walk on the moving sidewalk, you're able to pick up the speed quite a bit and make sure you catch the airplane or whatever else is going on there. And it's kind of a real life thing. This is, if I remember correctly, around 3 horsepower. Okay, so it's not a really big motor. You wouldn't want to use a really big motor. If you used a really big motor, A, it would go too fast, and B, it would spend a lot of energy. You want to use the lowest powered motor you can, so you're not burning up a lot of electricity. We don't need tons of force, but we do need some force to move this person along. Now, if we remember, power, and I'm just going to work through the derivation again. Power equals work divided by time. Well, work is force times displacement over time, and then I'm grouping these two guys together, right? Which will give me power equals force times velocity, right? Or how fast we're moving there. So my power that I'm going to need is going to be my force. Now let's just plug chug here. In fact, let's just go ahead and let's substitute in. So I've got 2,100 watt motor is applying 1,050 newtons to this moving sidewalk to get it to move. That heavily depends upon the gear ratios and everything else, times v. At what velocity is it going to move people along? So velocity here is just going to equal 2,100 divided by 1,050. Or 2.0 meters per second, right? Which is a reasonable answer. You wouldn't want to whisk people along at some insane speed, 10 meters per second or whatever, down a moving sidewalk. You want to keep it relatively tame to where people, because remember, they have to accelerate up to speed whenever they put their foot on the thing, and they have to decelerate down to speed whenever they're getting off of it. So 2 meters per second, very reasonable. 2 significant figures right from this number right here. 3 sig figs here, but you have to take the least, so 2 significant figures. All right, so another problem that any engineer or builder might encounter. So the builder is building a house up on a hill, and we're told this house is 210 meters above the water main down below. So whenever a city is putting in water mains, they're going to run it down the main streets, right? That's where the main is going to go, and it's up to the responsibility of the builder. If the house owns this entire property, it's up to the house owner or the builder to then run a pipe, right, with the help of the city, obviously, from the water main to the house. All right, so the builder decided to build the house way up on this hill. Let's actually put that in 210 meters up in the air. And then is going to cause the water to go up. Now, the water main has pressure in and of itself, but we're going to neglect that for now. How high would the pressure itself go up? We're going to assume the water main is more like a lake here, just for the sake of easy calculations, not having to include the pressure that's there. Now, the builder wants to use a very not too large of a motor, a 373 watt motor. That's about half a horsepower. And once again, you'd want to choose a very low, the smallest motor you could. Reason for that is the motor uses up electricity. And so and it's going to be running all the time, the house is going to need water all the time, right? So if you choose a big honking motor, yes, it can push a lot of water really fast, but that's not the idea. You want to conserve as much power as you can so whoever lives in this house doesn't have some ridiculous power bill. All right, so he chooses a small motor just to get enough water up there. So we're pumping it up 210 meters above the water main. What is the rate of water flow that this pump is capable of doing? All right, so power is work divided by time. And work is force times displacement divided by time. And that force here, if we did a quick free body diagram, right, I've got force of pump, if you will, force of pump going up and force of gravity going down. And so this force is the force of the pump, right, that we're trying to push up. So in the y-axis over here, sum of my forces equals ma. I'm going to assume that we're going to pump this water at constant velocity. So I'll have Fp minus Fg equals 0, meaning the force of the pump is mass times gravity, right? If we're going to go straight up and down here. The other nice part is if we're neglecting friction, even if we weren't going straight up and down, remember work done straight up is the same as work done along a length of a ramp or a length of a hill, so we could still use just mg in this situation. So power is going to equal mass times gravity times delta y divided by T. What rate of water flow? Now, lots of times people think rate of water flow is a volume divided by time. Another way is mass divided by time. If you need to get between the two, the density of water is well known. It's 1 milliliter per, it's 1 gram per milliliter, right? So that would be an easy conversion. But I can just group these two guys together to get my rate. So power is going to equal, and I'm going to group them, mass divided by time, G delta y. Well, now this is just a plug-chug problem here. I've got a 373 watt motor, and I'm going to solve for whatever this mass over time is. So mass over time equals something, right, times 9.81 times my delta y. I'm trying to get it to go up 210 meters. So I just need to divide my 9.81 and my 210 to the other side. And I come out with 0.18 kilograms per second, or 180 grams per second. So then, 1 gram equal, 1 milliliter equals 1 gram there of water. So you can do that quick conversion in your head there. That's going to give you 180 milliliters per second. Now, that's all well and good, and it saves power, which is what the builder needs to do. He doesn't need a ridiculous power bill just because you live up on a hill. That would stink. Well, this is an issue, though, if you think about how much water this is. This is not enough, really, to flush a toilet. How many seconds does it take for your toilet to fill up, right? And so you don't want it to take forever to fill that up. You turn on the faucet, you want to have a little bit of pressure there in the sink, right? You're standing underneath the shower, you want to have a little bit of pressure there. So this could actually be a problem. This is not enough water per second, especially if two people are taking a shower at the same time. We're going to have problems, right? Or if the washer's running and something else. So a way that the builder could fix this is using the exact same pump so that he doesn't have to install a larger pump with a greater amount of power, is he could just install another water tank up at the very top. And so the pump actually pumps water into the water tank that is level with the house now, and then you can put that water from the water tank over into the house. That'll allow the pump to run constantly, and whenever supply or demand from the house for water jumps up, let's say two people are showering at the same time and the washer's running, the water's coming from the water tank in at a good rapid spot. Another thing that builders like to try to do is they actually do factor in, obviously, the pressure into the pipe. They don't want to build much higher than the pressure and the pipe can cause the water to reach. They do have to think about how much pressure is getting up there, and that they'll still have to apply some sort of pump to make sure that the house has enough water pressure. But they don't want to build higher than how high the pressure can cause the water to go upwards.